three-element based partition. All right. Elimination details. How to eliminate one of the two subarrays. We need to start with that special critical partition step. All right. In order to do that, here let's assume the solution function, because we need to call this function recursively. So for convenience, we'd better have this function defined first. So first let me describe this function. Here I call this function gen selection with two parameters. The first one, integer parameter, the rank number k. The second, our data array, A array. So very simple. But more important thing about this method, I need to describe its output. The output is very special. So we need to use the information, very important for our partition. So let's see, what is the output? The output should be an integer array. So why an integer array? So our input not necessarily integer array, right? So A array could be floating point or string array, not necessarily integer array. But our output must be an integer array. So why? So look at what we store in this output array. First, S of 0, we store the kth smallest, the element of the kth. So here, I didn't write complete thing. So here, it should be index. We know index is an integer. So we store the index of the kth smallest element in the original array A. That's integer, Then remaining elements. This is just the first element in S array. How about the remaining elements? Remaining, we store indices for those whose ranks less than k. Why that? So here you may ask me, why that? Because later you will see, in order to do recursion, we need to do recursion many, many times. We need this information. Otherwise, our partition, our recursion, we cannot implement some of the steps. So you will see in my next slide, you will see why we need this information. Okay? All right. Now let's do the partition. Let's draw a diagram to see how do we find that critical partition element. We start from our experience. So in problem solving, our experience is extremely important. So what experience do we have related to median problem? So we have one, find the median of a three-element array. That is very simple. Here, let's use it. We have this result, so let's use it. All right. So the question, how can we use it? Right? So now let's try, but the question is, how can we use it effectively? Right? So let me draw a diagram. But before we do that, let's choose the most convenient end for us. We do not need to worry about some of the details. So we use this method many, many times, so we know it works. It works well for us. So let's assume n equals multiple of 3, 3r. If n is not of this type, 3r, don't worry, we can get it around easily. Yeah, so that's why first make our thinking analysis easier. So we make this assumption. Okay. Now the diagram, let me draw like this. So I arrange all the array elements into, look at this, 3 by r rows, columns, right? 3 rows, r columns. So why I arrange that? Partition element. Keep in mind what is our goal? Finding the partition element. So this arrangement can help us to get there. All right. So, all right. Now, partition element. All right. So there is one special step we need to do here. Okay? Yeah. For each 3-element group, so here we have R 3-element groups. For each 3-element group, can we find its median? Right? So look at here. The first 3-element group. Can we find its median? It's easy, right? How many comparisons do we need? 3. Okay? 3. Just like sorting. So in this problem, sorting a 3-element array and find its median, we use the same number of comparisons for the worst case. Okay, remember that. All right. So, but that is the median for one 3-element group. Similarly, can we do the second one, the third one, each one, and all our groups? How about that? So we find all the medians. All right? Yeah. What's next? So after we get all the medians, all right. So before we go to the next step, look at what have we derived so far. After we find the medians, all these are medians, we get each 3-element group sorted, right? So the upper element is less than the median, the bottom element is greater than the median. So we arrange in that way. So for each group, we arrange in that way. Okay? All right. So we need that. Okay? All right. Now, what's the next step? Okay? So we collect a lot of information. And then we pay some cost. Because this step, we need to use many comparisons. So we pay some cost. All right. Next, use the median of the median. So what's that? The median. So look at here, we have R medians, total R medians. So the question, can we find the median of these 5 R medians? The median of the R medians? So look at this step. Median of the medians. This element is very special. That will be our partition element, the median of the median. All right, so next step. Right? Now we want to, look at how good is this median of the medians. All right, so we have these, the information like this at this point. So let's do more analysis. All right. For our own convenience, in our analysis, we want to, provide ourselves more convenience. So we assume this R equals an odd number. Why this is convenient? Because in that way, the median will be the one right in the middle. Okay? Yeah. So that will be easier for our discussion. So let's assume that. Okay? Then n equals 6s plus 3. Right? Now we use this notation. M star represent the median of the R medians. Okay? So there are R medians, median of the medians. M star. Okay? This step, remember, the median problem is another selection problem. So we can call the recurrence function in this step to find this median. Okay? Recurrence relation. Yeah. All right. Call the function recursively. All right. And now another important step. Okay. After we find a median, there is another important treatment we need to make in this step. So what's that? We arrange all the elements that are less than the M star to the left-hand side of the M star. How can we do that? So you may ask me a question. How can we do that? That is important. But why we can do that? Okay? Similarly, all the elements that are greater than M star element are at the right-hand side of the. Yeah. So the reason that's related to the output of the recursive function. The output, remember the output. In the output, this part, that the information we use, indices, for those whose ranks less than k, in this special situation, this k corresponds to M star. How about that? Okay? We know all the indices for this array. This is the current array. All the indices whose ranks less than M star. So that means we can select these medians to the left-hand side, put them to the left-hand side of the M star, okay? And so on. Okay? So that's why in our design, some small treatment, very important. All right, so after this, next, so we want to do, further analysis here. Okay? So next, the first question. We want to find those elements that are guaranteed to be less than M star. Guaranteed. So this is very important, this requirement. Guaranteed. So from the diagram, can you find those elements that are guaranteed to be less than M star? See? Okay. So here, let me draw that part. This block, look at the elements in this block. Okay. Are they guaranteed less than M star? So let me convince you. So why they are guaranteed? Okay. All right. For example, for this element, it is less than its own median, right? But we also know its own median less than M star. By the transitivity property, so this one less than M star. Similarly, for each one, we can use that transitivity property, so we can get it is less than M star. Okay? So how many elements in that block, in that circle block? 2s plus 1. Okay? Similarly, we can answer the second question. What are those elements that are guaranteed to be greater than M star? Okay? This block. Okay? The similar argument, but this time the element greater than the corresponding median. This element greater than the corresponding median, and its corresponding median greater than M star. By transitivity, so all the elements in this second block greater than M star. Okay? And we also have 2s plus 1 elements in the second block. All right. This information very useful in our partition. Next step, we will see. Okay. 3 remaining elements that could be greater or less than M star. For the remaining elements, we do not know if they are greater than or less than M star. All possible. So that number, that remaining element, the total number 2s. S here, S there. Okay? Total 2s. But how do we determine what are those elements that are less than M star? What are those elements that are greater than M star? We do 2s comparisons. We can do comparisons, right? Yeah. We can do more comparisons. Okay? So we do 2s comparisons. We can get that information. Okay. All right. So next, do the partition. Okay. Now this time, let's do the partition. Okay. All right. Let's draw another diagram. Here in this array, this M star in this location, and this is important location because it is in place. This M star element is in place. Okay. Why in place? Because the partition element must be in place. It is a partition element. Okay. M star is used as a partition element. Must be in place. Otherwise, how can you do the partition? Right? So must be in place. After that, so you will see why it is in place after we complete the whole partition step. Okay. Based on our analysis in the previous slide, all the elements in block 1, look at the block 1, they are at the left-hand side of M star. There are 2s plus 1 number of elements. Similarly, block 2 at the right-hand side of M star. The remaining, although before we do 2s comparisons, we do not know where are they, but now we know where they are. Yeah. So after 2s comparisons, we know there are little a elements. So we call 3a block. So the 3a block, these elements are at the left-hand side of M star. And 3b block, little b, this number, at the right-hand side of M star. So after we complete this, you can see we make the partition. Okay? Remember, we pay this cost. This is the cost we pay. 2s, number of comparisons. We pay this cost. All right. So now, after the partition, what should we do next? Okay? Now we get a partition. What should we do next? How to drop a subarray. Now we can drop one of the 2 subarrays. So let's see that detail. How do we determine which subarray we can drop? Okay? All right. After the partition, first, let's look at the k number, our rank k number. If k equals 2s plus a plus 2, the rank, this s is the rank number. Okay? All right. We know the rank number is in the range from 1 through n. 1 through n. Okay? All right. So now 2s plus a, so look at here, 2s plus a plus 1, and a plus m star, there is another one, right? So this one plus that one plus 2s plus a. So we get this 2s plus a plus 2. That's exact the rank of m star, right? That's the rank of m star. So that means this k corresponds to m star, so we should return the index of m star. The index in the original A array of m star. Okay? That's the case 1, the simplest case. Case 2, k less than 2s plus a plus 2. This time we call recursive function, gen selection of k. The rank, we still use the same rank number k, but our data is different. So our data, we select the C array, this one, okay? We rearrange the C array, and we use the location number. The first element, we use its location, so not index from 0. So here, for convenience, so let's refer, using the location number to refer to the element, okay? Yeah, but that's a small difference. We can adjust easily. Yeah, so the location number in the C array. So we get a small subarray. So we just call this recursive function in step 2. Step 3, k greater than 2s plus a plus 2. This time, when we call the same recursive function, we need to adjust k and our data. The k, we do subtraction. Yeah, because the left subarray are eliminated, including m star. All eliminated. Okay? So if you eliminate it, we only look at the right subarray. Do we also need to reduce the rank number? Yes, we need to reduce. So this is the rank number we should reduce. That's why we do subtraction here. So that's our new rank number. Okay? Then for the data, based on the location, numbers, we can get the remaining subarray. Okay? So we call the recursive function. Okay? So that's the whole procedure. How do we call this function recursively? Okay? So we complete this step. All right. Have we solved the whole problem after this? So not easy. We have done a lot of work. Have we solved the whole problem? Not yet, because we haven't done analysis on this algorithm. The analysis, if we do not do that important analysis, we don't know if this algorithm satisfies our requirement or not. So we complete this part, and the next part we will do analysis. All right.